You do. Thank you very much. Well, first of all, I would like to thank for inviting me here. I've never been to this area of Italy. It's a really beautiful scenery, I think, and I'm looking forward to this conference. I've been to Rome, though. I can recommend Rome as well. And I'll be talking about, I guess, maybe I'm a bit an overknown character on this conference here because I'm not using differential equations to solve the Forsman theory, and furthermore, I'm not really normally doing research on biophysics or biological systems. I'm more of a colloidal science guy, and maybe a bit of ionic liquids more recently as well. So with that in mind, I will try to talk to you a little bit about how you can approach electrostatics using classical density functional theory. Yeah, I should start by saying that, by the way, most people, when they hear density functional theory, think about quantum mechanics. This is all statistical mechanics, so the functional that we treat is a free energy and not an energy, and the densities are not electron densities, but more like densities of solvent particles or ions or monomers in a polymer or something like that, something more, well, larger than electrons anyway. So this is the basic outline of this talk. First I'll talk about DFT, which is our acronym here. And for those of you who have some background in DFT, it will be very trivial, I'm afraid, so I have to apologize about that. So this will be very basic stuff here. And then I'll show you how to, it's very easy to just write the correspondence of Forsman in DFT language, if you will. I'll talk about what I believe is some of the advantages and disadvantages of DFT compared to the differential equation approach. But keep in mind then that I don't really have any experience in solving Delphi or anything like that, so I'm just guessing what's good with DFT or bad. And then I'll talk a bit about a few simple examples and some geometries that we have been using in the past, and then I'll also show you what we can do beyond the mean field. So that's, I guess, one of the advantages of DFT. It's relatively easy to include approximations that will help you take into account ion correlations. As I mentioned, I also do some stuff on some research on ionic liquids where the ion correlations are really strong because they're almost freezing, right, or on the brink of freezing. So here's a bit of really basic stuff for DFT. Here you might recognize the configuration and integral. This is, of course, our holy grail in StatMech. This is what we want more than anything else. But unfortunately, we can't solve this integral. It's kind of hopeless. So we have to do a bunch of simplifications. If you stay with simulations, you can essentially stick with just using, well, this is at least one of the simulations to assume that you have pairwise interactions. And if you have reasonably accurate pairwise interactions, then you can stay there and you can do simulations and you're fine. I mean, with that approximation. But if you want to go further, for instance, to the Forsman level, you also have to invoke a mean field approximation. And here I've written the mean field energy per particle. So you consider yourself located at a particle at the origin. So at the origin there's one particle in a bulk fluid, let's say. Now the particles in the bulk fluid, they interact via a pairwise additive potential 5r. So that depends on the distance only. So it's a spherical symmetric. I assume it's a spherical symmetric interaction here. Now given that, and we have a bulk density of n, which is simply the number of particles per volume, right? Just the density. Then the mean field expression for the energy, interaction energy per particle is this integral is a volume integral of the interactions, and then you have to multiply by the density. I guess, yeah. And then there's this factor 1/2 to account for the fact that if you don't have it there, you sort of double count the interactions, right? So you need that 1/2 to avoid double count, because otherwise you could locate yourself on another particle and then you sort of count that interaction twice. So if you multiply this by n, you get the mean field total energy. Right. So both of these approximations or simplifications are rather extreme. I mean, without the pairwise additivity, we wouldn't get anywhere. And it's really a nice simplification. But also this other mean field assumption is simplifying things a lot. This is then the total mean field energy, and suddenly we can write the mean field expression for the configuration integral. And then you see you can lift out this becomes a constant in the bulk. So now you have a constant rather than that messy integral we had before. So rather than having this, which is horrible, we have something really simple. And that means that we can just perform this volume integral. That's just the volume raised to the power n, right? And then we write out the mean field energy, which is this. So now we have an analytic expression for the configuration integral, given that you have some additive. This could be a Lennard-Jones potential or indeed just the Coulomb potential, right? And the corresponding mean field Helmholtz free energy is just the logarithm of that. You have to take into account this n factorial, of course. And then you get the ideal term here. This is the ideal entropy and the interactions. So you have entropy and you have energy. And this is, yeah, the n is just the density. So it's as simple as that. But we can actually do better than that. And that was some of these improvements were done by Sture Nordholm in the early 80s. And if you do better, of course, one of the best things you could do, given the assumption of pairwise additivity, is to actually introduce the radial distribution function around our tagged particle. That would be really nice. The problem, of course, is that normally we don't know this. We don't know the radial distribution function, typically speaking. A simple choice, approximative choice, would be to say that, all right, we know that in the vicinity of our tagged particle, there will be no other particles, because the tagged particle will expel, due to just simple exchange repulsion, will expel some of its surrounding, right? And then we can say, all right, let's assume we have a step function here for g of r and plug that in here. It's like a hole surrounding the particle. That will then, of course, if you consider a dense liquid, like a Lennard-Jones liquid or molecules, then you cannot just, or you can, but you shouldn't just include this difference or this change of energy, but you should also consider that this will actually reduce the available volume for the particles in the system. And that means that you will actually pay an entropy penalty, which is down here. Right? So the volume is not, the available volume for the particle is not the total volume, but the total volume minus n times the volume per particle. It was really Van der Waals who started this idea of thinking, I guess. And if you do that, then you can get an expression like, which is in principle then for a liquid better than the one we started with, right? And this is enough to predict typical Van der Waals loop and gas-liquid condensation and so on. And then if you again consider Lennard-Jones liquids, you can proceed further with DFT and you can have what's known as non-local densities, and you can describe oscillations in fluid phases and so on, which again was developed by Sture Nordholm. But normally, we're not interested in just the bulk phase. I mean, you can be, but normally, at least in my field, and I guess in yours too, we're interested in the distribution of ions or particles or something in a heterogeneous system. So then we have to consider that these densities vary in space. And then you have to express the Helmholtz free energy as a functional rather than a function of the whole density distribution. And the difference between a functional and a function is that the functional is like a function of a function. So it's a function of all of the density distributions, not just the density at one point or something like that. But other than that, it's kind of the same expression. We have the mean field expression again, entropy here, energy, but then typically speaking, we have to also add some interaction with an external field emanating from a surface or a particle or a protein or whatever it is, right? So here comes, essentially you can say that the system description is in here, right? And then you have your interactions. Now, again, if we have a heterogeneous system, we normally, or usually at least, consider a system where there is some sort of bulk solution in. around, so that the system is in equilibrium with a bulk solution of a prescribed chemical potential. Now then it's convenient to transform this Helmholtz free energy to a ground potential, which just means that you subtract this term, and you have, I should also point out that this chemical potential is of course a constant, so you could as well put it outside of the integral if you like. So this is like Helmholtz free energy minus number of particles times the chemical potential essentially, right? And the optimum profile is the one that minimizes this ground potential functional then. And that means that we set the ground potential functional equal to 0 to find our solution. And as a really simple case of this, we can look at an ideal gas in some external field. School book example, I guess. So that then we know the chemical potential, first of all. That's just the logarithm of the bulk density, because it's an ideal gas. And we can formulate the ground potential for the ideal gas. Again, we have some density distribution. This is the entropic part. We have the interactions with the external field and the chemical potential. But now there's no interactions because, again, ideal gas. Putting this ground potential functional, if we evaluate that, we see that that becomes the logarithm of the density normalized by the bulk density minus this external field. And we should minimize this, so we set this equal to 0, meaning that we get this expression for the density, which is of course all just the Boltzmann distribution, of course, which is what you would expect. So for ideal gases, you immediately arrive at an analytic solution for the density. But normally that's not the case, right? Normally it's not that simple, of course. In my field, at least, the system I tend to look at has some symmetry. I realize that for proteins this can be a bit different, but in colloidal science things tend to be a bit easier than in biological science. So we have like spherical particles, or we have rods, or we have something which is prone to some sort of symmetrization. I will come back to that. So a few cases that we that you easily normally study is distributions or adsorption or whatever around some single sphere, in which case you can integrate out 2 dimensions, leaving you with a density function that only depends on the density in one direction. So it's like a one-dimensional problem then. Similar, if you have flat surfaces, there might be some bulk around here somewhere out. But in principle, you solve for the density in just one dimension, integrating out 2 dimensions, leaving you with a one-dimensional problem again. If you have 2 spheres, then you might enclose this in some cylindrical geometry, and then you're left with 2 dimensions. But these are still calculations. I'd say for these cases, a calculation takes typically maybe seconds, and this might be minutes. So it's kind of fast calculations anyway. But if you go to 3 dimensions, it's a different beast, though. So let's then focus on the Poisson-Boltzmann equation, or charged systems. Well, it's relatively straightforward. Just take the function I showed you before, the mean field functional, because Poisson-Boltzmann is a mean field theory. And then you plug in the entropic part, and of course then you typically have, like, if you have Poisson-Boltzmann, you expect like 2 components, like a salt, typically speaking. So normally you have at least 2 components here, so you have to sum this. And then again, you have also the interactions between the 2 components, just plugging in then a pairwise additive potential, which is just a Coulomb potential. And then you might have some external field from charged particles or surfaces or whatever. And that's more or less all there's to it. And I'll just exemplify. If you consider then a slit geometry, then again, for each Z value you choose, you assume that the ion distribution is uniform. It just has a value there, right? Yeah, so there's no heterogeneity in the XY directions. That's the assumption in the slit geometry here. And then you get the entropy term here. You get an energetic term with a Coulomb potential, and you get the external field. And by the way, also I should say, if you consider the chemical potential, as we do in the next slide, that's also just the ideal term, actually, because in the bulk, according to Poisson-Boltzmann, there's no interaction, no net interaction. in a bulk solution. The Coulomb potential looks like this. In order to get this Z-dependent Coulomb potential, effective Coulomb potential, you have to integrate out 2 dimensions. And if you look at this integral here, you will see this is, by the way, the Bjerrum length here. And here I've also assumed that we just have monovalent ions. If you look at this integral, you will see it's not convergent, it's actually divergent. And that's a typical problem in electrostatics. It takes care of itself because you have to ensure that things are electroneutral. So all these infinities will cancel out. And you're left with this, effectively, you're left with this potential between the ions in this particular geometry. And if you do the ground potential minimization, you get something like this for the distribution of the alpha ions here. Here I've actually included explicitly, we don't have to do that, but I've included the interactions between the surfaces because you have to consider that when you consider, let's say, the net interaction if you have 2 surfaces. And that would be the net interaction between them because then they might have a charge density here. H is the separation, so this is just a constant term, not very relevant for the interactions themselves. We do have to make sure that the system is electroneutral, so effectively we change the chemical potential of the species such that one of them has, you could say, effectively higher chemical potential, the positive ions, let's say, and the negative ions might have a lower chemical potential, but the salt itself has a constant chemical potential. So we need this Donnan potential then to ensure electroneutrality. And then we have this part with this in the interactions of the system with of the ions between each other. This is then solved iteratively, and of course there are many ways to do that. I tend to just stick with a simple Picard iteration, meaning that you solve this and you get a new distribution, then you plug in, you use some of the old solution and mix in some of the newly predicted ones, and then you keep going until you get self-consistency. But of course there are many ways to do that more efficiently. You can think of some sort of Newton-Raphson scheme. I've tested that as well, and Newton-Raphson, for instance, works really nice if you're close to the solution, and then you get the answer in like 1 or 2 iterations. But if you're further away, it's not very stable, so I have to be careful there. I guess there are other ways. I've seen you can use something called Boyden's method, I think, and so on. But I've not really optimized this myself because I have never encountered problems where I need to put in a lot of CPU effort. Right. So here's a list of what I reckon might be advantages of the DFT, but I'm not exactly sure. If you agree with me, I think it's nice to have like everything expressed in terms of the free energy. For instance, you can use consistency rules to check your code. So for instance, you can use something called the contact value theorem, meaning that if you have a bulk solution and let's say you just have a hard wall, then the contact value should reflect the osmotic pressure of your solution. So it should be a consistency between whatever density you have in your bulk solution and the contact value you have at the surface. Or equivalently, as we will see, you can also look directly at the force curve itself if you change. Because we're often interested in my work of interactions in between particles or surfaces in colloidal science. Now, having access to the free energy is also convenient for phase equilibrium problems. And since you have explicit molecular interactions, it's very easy to extend to include hard sphere repulsion, dispersion. You just add that to the potentials, right? So it's not very difficult to handle those cases. And charged polymers, I think this might be one of the perhaps most important advantages, is that you can treat polymers. Like you have a charged, let's say you would have a charged protein then, or charged something, and then you have a solution of polyions or polyelectrolytes. Then you can treat that with DFT. And even if it's polydispersed, which is actually one of the, usually as I said, the colloid science is easier than biology, but in this case, I guess polydispersed is something that you usually get away with in biology because most proteins are monodispersed, right? But in colloid science, the polymers are usually polydispersed. And that you can treat also. You can have a polydispersed polyelectrolyte and treat it easily with DFT methods because we've developed some methods for that. And you can treat titrating polyions or polyelectrolytes, but also, of course, titrating just ions if you have simple ions as well. That requires you to have a two-state treatment of the molecules. And then it's also relatively easy to make approximations of ion correlations, and I will show you some examples of that. Well, one can also in principle combine with Monte Carlo and get an improvement of intramolecular correlations in polymers, for instance. Disadvantages, well, I'd say that it's not so widely used, so you wouldn't find too many softwares that you can download or so. There's one called Tremonto, which has been built by Gillespie and co-workers, I think. And it's been recently, I think, also extended to handle 3D cases, like, for instance, a protein or something really heterogeneous when you have no symmetry at all. I'd say, though, that most likely programs like Delphi or so are a bit more well developed in that area, although I don't really know. But in principle, of course, you can solve DFT in 3D as well. So I'll walk you through some examples, and then we'll see if I can highlight. Maybe you can decide for yourself if DFT is something for you or not. First, I'll have a look at some cases we looked many years ago on phase equilibrium in lamellar systems. And then a very simple example of pair interactions between charged particles. I just chose this because it's so simple. I don't think anything really came out of that. And then a bit more advanced, if you look at interactions between charged particles in polyelectrolyte solutions, that's not as trivial though, and also polyelectrolyte adsorption. So as a first example, we considered maybe, I don't know, 7 years ago, so the interactions, the phase behavior of two different kind of bilayer systems. So this is like a amphiphilic molecule, and then you have, this is then charged, right, positively charged, and this part is then the counterion to this amphiphil. And it turns out that if you have bromide as counterion or chloride as counterion, that matters a lot for the phase equilibrium, or phase diagrams of these systems. And one hypothesis is that we had is that maybe the bromide is adsorbing with some specific non-electrostatic interaction to the surfaces. And we sort of started with that hypothesis, and we worked our way from there. And we looked at, actually we looked also at higher salt, but I won't cover that here. So we actually assume that we have only counterions to the surfaces. Now CPB, as I will have, is an acronym which is called correlation corrected Poisson-Boltzmann. I will get back to how you can do correlation corrections. For the time being, you can just assume that there's some sort of correlation corrected included there. So the kind of systems that you will see, or that people see for these bilayers, is that you have one phase with a very narrow water phase, and then you have the oily phases here. And then there's another, this is called L alpha, I think, or if it's L alpha prime, I don't remember. And then there's the other phase has a much wider region of water here, with counterions then, of course. And then you have the charges here, the charged Higgs groups and the oily phases. If you have chloride as counterion, however, you never see this phase separation. It's actually then a first order phase separation between this and this. That doesn't happen for chloride as a counterion. So our assumption then is that maybe the bromide will adsorb a bit more strongly than chloride. So we simply dreamed up a short-ranged potential. So this is like a Lennard-Jones surface, and we added some extra bit to it to make it more short-ranged. So this is then in ångström, and you see the range of the potential is a few ångström, I guess. And we had two different, I just showed two different amplitude factors, really, you could say. This has been 1/2 kT in depth, and the other one being -1 kT in depth. So this actually represents our model of chloride, and this our model of bromide. That's simple, really. And here I'll just illustrate that as a useful check of your code, you can make sure that the pressure that you measure between these bilayers can either be found by integrating the force given your equilibrium density distribution, or you can take the ground potential that you evaluate and make a discrete derivative. And these two should match, otherwise there's something wrong. It's very sensitive, this. So if there's anything wrong with your code, they don't match. And it's sometimes this is called the contact value theorem. So it's a useful rule, a consistency rule to use. Now, if we look then at the Forsman predictions of how the pressure varies, the osmotic pressure varies with separation between the surfaces, then you see you'll have, depending on how you choose this non-electrostatic absorption, you can have different kind of behaviors. And when this is strong, it's actually dropping down to zero, even a little bit below zero. And this is weird for a Forsman treatment, because normally you can't see attractive pressures without having something correlation-like. So that's just different choices of this. Of this value here, of the depth of this non-electrostatic potential. So that corresponds depending on how strong that is. And the reason that you can actually see even attraction here is because actually, even though we made it short-ranged, it's the range of this potential. If this was strictly short-ranged and truncated somewhere here, you would see that that minimum, that negative pressure, because the negative pressure comes about from particles or ions on one side of the midplane. If you look at midplanes here, on either side of this midplane here, interacting with the other surface. So that's, in a way, is a bit unfortunate. However, if you include correlations, you can actually get this minimum without such maybe artificial or erroneous kind of feature of the potential. So here we looked at Monte Carlo simulations, and this correlation corrected Forsman for how the osmotic pressure varies with separation, given these different non-electrostatic absorption potentials. And as I said, you do see this attraction here. That would be here even if we had used a strictly short-ranged potential. They do deviate a bit here, but otherwise this correlation corrected Forsman, which I will get back to, seems to work okay. The Forsman, however, is not very accurate for this system. So if we look at the phase behavior, then the theory predicts this curve here, because, I should have mentioned that. You can then construct from this a van der Waals, a Maxwell equal construction for the two phases. One will be far away here somewhere, and the other one will be roughly here, I guess, depending on which depth you have of the non-electrostatic part. So the prediction for the phase equilibrium, or the phase, or the response of the system to increasing the osmotic pressure, which they do in experimentally as well, by the osmotic stress technique it's called. They increase the osmotic pressure, and then you see a phase transition. In the experiments, this bends off here a little bit, which it doesn't in our theory, and that has to do with, mostly I think, that our theory is treating the bilayers as completely rigid, so there's no compressibility at all in them. And at such high pressures, I guess that you will have some compressibility effects. If you and that's our representative of bromide, and if you'd have chloride instead, you'd see something like this, according to our theory. Experiments show something which is almost like a phase transition, but not quite. So there is this a bit of wiggle here. So that's anyway, that's one illustration of how you can use density function there. This is even more simple, I would say. This is just looking at charged particles, charged spherical particles in a solution. There was a colleague of mine who wanted the potential mean force between these to predict some structure factors, I think. So he was going to use the potential mean force extracted by simulations of Forsman, and then use them to simulate a system with then this kind of potential mean force between particles to evaluate structure factors. I don't know if anything came out of that. I don't know exactly what he did with that. But I thought it was a nice illustration of a simple case where you find ion distributions around charged particles using the density function technique. And here we see then Forsman versus Monte Carlo, and Forsman will always be more repulsive. That's because we don't have these ion correlations. So the ion correlations always will tend to make these forces less repulsive. And then you can fit something Yukawa-like. If you know about DLVO theory, you know that it will predict, or it assumes that these colloidal particles like that will repel each other by well, from the electrostatic parts, it will be like something like a Yukawa potential between them. If you try to fit the charges that you know, and the pi length that you know is here, it will be really lousy, so that it simply doesn't work. You have to renormalize the effective charge of these particles, and that's something like people like Alan Denton has done, devoted quite a bit of work on. And then we have again an illustration of the contact value theorem. I show it again because it's kind of useful to check your code here. Also, when you have polymers, you have the same kind of trick to check that it's consistent. So here you have evaluated the force directly, as, I mean, just measure the force between the particles given the interactions you have in the system, or else you can work out the ground potential as a function of separation and then just take the discrete derivative, and they should agree. Now, this, as I said, this is a really simple example. This is much less simple because here we have polymers and charged particles, and this we have then tried to simulate, but also treat by density function theory. And this is a highly non-trivial case. I assume that this would not be easy to treat with like differential equation approaches, but I might be wrong. So we can then use our mean field DFT to handle polyelectrolytes because there is a polymer version of DFT. And we shall denote that as PPB. The PPB turns out to be very inaccurate, and that's because the ion correlations are so important when you have connected ions like that, as I will show you. So that's called connected monomers, I call polyions. So when you have polyions, you have to include some sort of approximation of the ion correlations. And the ion correlation version of PPB, which I will describe shortly, I will denote as DFT. I will just first show you that it's important to have these correlations. Now what happens when you have a system like this, if you look at the interactions, these are then, let's say, negatively charged particles, and you have a solution of positively charged polyions, and of course also a simple salt. What happens is that the polyions will, assuming that you have some sort of bulk, they will always absorb so strongly that they actually overcharged the particles. So there will be more polymers absorbed there than is required to neutralize the colloidal particles, and they will behave as if they have a reverse charge. And that leads then to a double layer repulsion between these overcharged particles at long range. At short range, however, you get polymer bridging and ion correlations, which generate a very strong attraction. Now the PPB here, the mean field, the pure mean field, will only capture this bridging part of this problem. So it will fail to capture the overcharging and the double layer repulsion. So this is just simulations here. Here we see the colloids have a radius of 4 nanometers, a charge of 86. Here we have simulated a few cases where we have no salt. And then we have added some, and this is also, I should say, explicit model. I'll come back to it. Here, all the ions are explicit here. So we have explicit monomeric ions, we have explicit charges on the particles, and also the salt particles are explicit. And then we add some simple salts, simple 1,1 salt, and we see that we can screen away this barrier here. We can screen away the double layer repulsion as one would anticipate. This is then the force, this is then integrated to get the free energy, and the free energy might look like this for such small particles. For larger particles, of course, this barrier is much, much higher. But we can also see that what happens is that it's not as if you just salt out the original colloidal dispersion. You get something which is much stronger. The attraction here that results when you add salt is much stronger than a typical just van der Waals attraction that you would find otherwise. So there is a point of adding the polymers, actually, if you want to flocculate, that is. So we can also simplify the system. I mean, these simulations are pretty heavy, so we can treat all the monovalent ions, collect them, and treat them just implicitly via the screening. So we work out the Debye-Hückel length corresponding to just whatever kind of simple free monovalent ion you have in there, and you work that out into a screening length, and then you then you consider only screen-Coulomb interactions between what is remaining, that is the connected monomers, and if there is any multivalent ions around, you have to treat them explicitly as well. So you have to be careful that the ionic screening then that you put in, the debye length, is provided by the implicit simple monovalent ions only, otherwise you double count. And then we can compare then the explicit model, this is all, again, all simulations here, with the implicit model, and we see that it seems to work all right with our perspective and kind of glasses we are using. This is more or less the same free energy curves you get for different levels of salt. So we are pretty happy with the implicit model because it saves us a lot of computer time. And then we can proceed and look at look at what happens if you actually add a divalent salt instead, again comparing the explicit model with the implicit one, keeping in mind that in the implicit model all the monomers are there explicitly, and the divalent ions here are there explicitly. And what we see here is that for a given debye length, it's much more efficient to add counter ions to the polymer divalent ones. That is, these are co-ions to the particles, that is. If you want to flocculate, that is. You will reduce the barrier much more efficiently given if you provide the system with divalent ions. But still, the explicit and implicit model works fine, and the implicit model is actually a very convenient alternative using just a Yukawa potential between the monomers. So then we compare DFT, which then you remember contains also correlations in some way with simulations, and we see that the prediction is not too bad. The barrier hence tends to be a bit further out than predicted by simulations. But other than that, the predictions are pretty good. And here we see again, if we add a lot of salt here, we see a strong bridging and correlation attraction at long range, much stronger than predicted by van der Waals attractions. If we, however, just use the pure Forsman equation for the polymer, we will predict something like this. That is, this is a case where you should have a strong barrier and you don't see any barrier at all, because the mean field is simply not good enough for these systems. So if you have polyions present, you cannot, or you can, but you will end up with very erroneous predictions if you treat it by just mean field. So why is mean field so bad? Well, again, it's the neglect of correlations. As I said, if you locate yourself on one ion and you look at the surrounding, then in the mean field you integrate everything, assuming just a constant density. But in reality, this ion will actually exclude a part around itself. Primarily, then, the important part is the exclusion between like charge ions. So the main failure of the Forsman theory is that it overestimates the repulsion between like charge ions, because they will never be in the vicinity of each other. They will never be close. So then you can use some simple tricks to account for that. First, we see here that the mean field energy per particle in principle contains a self-interaction. A part of this integral here comes from the particle itself. So then you can assume that, all right, I will exclude then a spherical hole around my TAD particle such that it actually, this integral just excluded one particle, namely the one you're located at. Now, that will be then a rather, you can do that, and that will lead certainly to improvements, but a more realistic assumption is that maybe if you look at G of R between like charge ions in a typical solution, it is more soft, like it's not like a step function. So a more realistic alternative is that you assume that it approaches unity wise, it's got an exponential decay from increase from zero. And if you assume then a soft exponential hole, you put it on the same kind of normalization, then you find this energy, corrected energy per particle instead of the mean field version. And you can make things even simpler by assuming that this lambda, this decay length, is position independent, so it's only depending on the bulk density, and then you get something like this, which is really simple. And that's one we have used, actually. And using that, we get a very nice agreement between simulations and theory. Now, I'll finish off by looking at some results we have for polyelectrolyte adsorption. So then we have a negative surface and a positive, if you like. The polyions are positive, the polyelectrolyte is neutral. That will lead to overcharging. What we have been interested in, both with experiment and theory, is how the adsorption changes when you add simple salt. And there are two competing effects. If you add salt, you will screen away the attraction that the polymers feel to the surface, but you will also screen away the repulsion between adsorbed polymers. So one will favor the adsorption of more, will sort of disfavor the adsorption of polymers. I mean that you screen away the attraction. But then again, you also have the screened interaction between the adsorbed polymers, which works the other way. I'll skip this actually. And this is a simulation of a particle of a radius of 1000 angstrom and some charge. I don't remember the charge, it's pretty highly charged. But on the other hand, the charge density, I think, was something like 1400 angstrom squared per charge. It's not very highly charged if you look at it as a surface charge density. And then we had 160 moles, each of them charged outside, and we had an outer spherical surface in the simulation and some salt concentration. And this is the density profile then. So we had, I think, 180 of these. So these were pretty heavy simulations, actually. And then we got density profiles looking like this. You get a strong peak. It depends on the concentration of salt here. We're using now the Yukawa approach. So these are just, the simple salt is implicit. We get a correlation such that first you overcharge the surface, then there's a regime here where the monomers, or the polymers if you like, are essentially absent, especially at low salt, and then you have like a bulk here. And the bulk will unfortunately vary in the simulations. You try to keep it as constant as you can, but it will have to vary a little bit. In the DFT approach, of course, you set the boundary here. There's no outer surface, and the bulk is well known because that's an input parameter in the DFT. And the DFT will underestimate a bit the adsorption, and this is with correlations. And the correlations will also provide you with this Coulomb hole here. By the way, this is where if you have what people call multi-layer adsorption, this is where the polymers of different sign would adsorb if you were to add them. Then you can build up what's known as polyelectrolyte multi-layers. Here also some density profiles just showing different lengths. This is kind of the final outcome, the important outcome of this study. So we saw that we have shorter chains and longer chains, and we see that first there's an increase as you add. Remember now that there's no non-electrostatic part to this. First there's an increase in adsorption, and then it drops quite drastically above some threshold salt concentration. That threshold itself depends on the length of the polymers, at least up to some. I mean, it saturates eventually. But there is a regime here where the polymer length dependence is quite drastic according to simulations as well as DFT. So we can illustrate that by a graph here. If you have the particle being shown by, it's actually shown by the polymers around it. This is a snapshot from the simulation. At low salt and long chains, it looks like that. If you add some salt, it will look a bit more fluffy, but you'll still have a significant adsorption here. If, however, you have these 40mers instead, again, strong adsorption at low salt, but when you add salt, you can't even see the polymer, the particle anymore because the adsorption is so weak. This is actually something we quite recently have verified experimentally by ellipsometry. So there's a student of mine who's studied with ellipsometry adsorption of short and long chains, and it seems to corroborate this prediction. Now again, I just have to point out that if you were to treat this entire system with mean field approach, you will fail to discover that you actually have a regime here where the adsorption increases first before it drops down. You will predict just a monotonic drop of the adsorption, which is erroneous. Right, I think is it time now? I'll skip. All right, this is just showing that we also made some comparisons with experiments that we had to include a non-electrostatic adsorption potential, because in real life there's always something hydrophobic or so that adsorbs, unfortunately. And but we got a really nice agreement between experiments and theory, with some deviation here, which I think in part depends on errors in experiment, actually, not in experiments as such, but in the way the angles from the ellipsometer is interpreted and transformed into adsorption. I won't dwell upon that. So in summary, I think that the DFT approach is kind of the main advantage is probably versatility, right? So you can treat polymers, polydispersed systems, many different kinds of interactions, And you can also make physically simple estimates to include ion correlations here. And usually the simple estimates are enough. I mean, you just say that, all right, we know that there must be some Coulomb hole surrounding a particle, and then that's enough. Ionic liquids are a bit more tricky, though, I must say. That ionic liquids, you have to worry about everything. Right, and then I'd like to acknowledge, this is like a chronological order. Martin and Cliff and Torbjörn, they were involved in some early simulation studies, which I haven't really talked about here, with polar electrolytes. Sture Nordholm and I worked on this simple correlation corrector, and Faye, she has done the experiments that I only briefly mentioned, and her experimental supervisors are Tommy Nylander and Lennart Piculell. I thank you, VR and OMEM, for funding. I forgot to put up the organizers. I thank them as well, of course, and I thank you for attention.